Hi folks, this is the first video for Unit 3. We are starting in with Unit 3, Day 1, and this lesson is Equations of Lines in R2. Now, you might be thinking R2 is just the regular XY coordinate system, and we've been doing equations of lines on the XY axis since grade 9. And you would be right. But what we're going to do is extend the work that you know how to analyze and graph a line in 2 dimensions. And now we're going to start learning how to define that line in terms of vectors and position vectors and direction vectors in R2. So let's just start with graphing this line. 3x minus 2y plus 6 equals 0. So this just using any method that you know from earlier grades. Maybe you want to find the intercepts. Maybe you want to put this in y equals mx plus b. We could do kind of either method here. So negative 2y equals negative 3x minus 6. And then dividing by negative 2 all the way across, we get y equals 3 over 2x plus 3. You could also look at this as finding the intercepts. So the x-intercept would be 3x minus 2 times 0 plus 6 equals 0. So the x-intercept would have 3x equals negative 6 or x equals negative 2. The y-intercept would have 3 times an x value of 0 minus 2y plus 6 equals 0. Negative 2y equals negative 6 and y equals 3. So you can use either method. We're going to get the same graph, of course, both ways. So we will put a y-intercept of 3, an x-intercept of negative 2, or using a rise of 3 and a run of 2, of course, you get the same line. So I'm going to connect my points here, draw that, and label it 3x minus 2y plus 6 equals 0. Okay. So that's how we graph lines. We know how to graph lines. We want to start thinking, though, about lines in terms of vector representations. So the first question that might help you kind of zone in and consider that is, what is a vector along this line? So I'm just going to draw in here. And probably between these 2 points is the most obvious one here. One of the most obvious ones there. So this blue vector that I'm drawing in here, it's going an x component of 2 and a y component of 3. So I'm going to reorient this vector. Remember, as I've said a lot of times, vectors have magnitude, they have direction, they do not have a location or a position. So that is the vector 2, 3. So it's going a component of 2 in the x direction plus 3 in the y direction. And of course we could write that as 2i hat plus 3j hat, but we're going to more often see this in component form. So we want to figure out a way of writing the equation of a line, of this line, using vectors. So hopefully it will make sense to you that if you are at a point on the line that you can get anywhere else on the line by adding a scalar multiple of this vector that goes in the direction of the line, and that's going to be called a direction vector. So I'm just going to write that out. So from one point on the line, we can get to any other point by adding a scalar multiple of the direction vector. So if we knew one point on the line, we can find all the other points. All of the other points on this line can be defined as that first point plus a scalar multiple of the direction vector. And that's what we're going to use to come up with what's called the vector equation of a line. So this is the formula for the vector equation. And I'm just going to kind of draw this out in general. I want you to kind of see it visually, and then we'll walk through what that equation actually means. So if I have a line, there's my line. We don't know. I'm going to do this kind of in general without using specific points. So the first thing I need to do in the equation of the line is to find one point on the line. So I'm just going to put a point there. I'm going to try and keep this pretty general. So the first thing to get to any of the points on the line is to get from the origin to a single point on the line. And remember, if we go back to the original equation, this equation is a definition of what all of the points on that red line would satisfy. We could find every point on the line by saying 3 times the x value minus 2 times the y value plus 6 has to equal 0. Any point that satisfies this equation is on the line, and all of the points on the line will satisfy this equation. We can find all of them using this equation. For different x and y values, if it satisfies this, it's on this red line. So that's kind of what we want to define in a vector form. I want to be able to find any point on here using vectors. So my first step in this is to get to the line. I have to get somewhere on the line, and then I'm going to draw in this blue direction vector. If I know some vector that's in the direction of the line, I can add a scalar multiple of this. So if the purple vector gets you from the origin to a point on the line, so one single point, so this is going to be point P naught. The little 0 there is sometimes called a naught, and it means like an initial. So that gets me to some initial point on the line. Sometimes you might know the y-intercept, but that's not always the case. So I'm drawing it kind of in a general sense there. And then if we know a vector that goes in the same direction as the line, I can add from this point P naught, I can go any scalar multiple of direction vector m this way, and I can go a negative scalar multiple of it and get to any points on this side. So this combination of the starting initial position P naught plus this direction vector m will get me to any point on this line. So that's what we're going to do. We're going to say, so this is vector r naught to get from the origin to point P, and that this will give me a resultant vector. So I'm going to take the r naught plus vector m, or some scalar multiple of m, and that will get me a resultant vector that gets me to any point. I'm just going to kind of hop over there. This resultant vector will get me to any point on the line. So I might need to multiply by a negative to get to the other side. And this is the general form. So we can get a vector to any point on the line if we take an initial point on the line, that R naught that goes to this one single point, plus a scalar multiple t times the direction vector. So it's a lot of new notation here, and that's kind of why we start today with just R2. It's a little bit easier to visualize, and then in tomorrow's note we're going to be doing the same thing in R3. So the vector equation, a general vector to any point on the line. We get that by taking R naught, vector R naught. So this is from the origin to point P naught, and this is a vector to any specific point on the line. And once we get to that specific point on the line, I'm going to use this t, scalar multiple t, times vector m, where vector m is a direction vector in the same direction as the line. So this is a scalar multiple So m goes in the direction of that line. So I like to kind of use a bit of an analogy here. If you were, say that you wanted to get somewhere, and just kind of taking this off the XY axis. Say you wanted to get somewhere along this road. Here's a road. Okay. You are at a point here in a field, and you want to get somewhere along this road. We don't know where. You could get to any spot on that street if you first walk to the street, right? Your first step to finding a certain house on that street is to walk to the street. That's our vector R naught. We got ourselves to the street. Then you can walk along the street kind of as far as you want, and as long as you stay on the street, you could find all of the houses on this street. So then you've got some scalar multiple of the direction of the street. You're going to walk some distance along here. A scalar multiple of vector m. And that will give you your directions, or your vector, going from your original point, from your origin, to a certain spot, to a certain house on that street. So it's really important to recognize here, the first one that doesn't have a scalar multiple, that's getting you to the line. That's a point on the line. And the second vector is going to be the direction of the line. That's like get to the street and then walk up and down the street to look for the certain house. So that's what we're going to be using as our vector equation of a line in R2. So if we have this vector equation, I'm just going to rewrite that out. The vector equation is R equals R naught plus t times m. And we know that vector R is x, y, and that's any point on the line. So that's finding a point on the line. And R naught is the direction vector, or the position of getting to a point on the line. So this is a specific point on the line. And M is the direction of the line, and we use A, B as the components there. So one way of writing this is to kind of break this apart. Instead of having here like x, y equals, I used purple for this, x naught, y naught plus t, and then this was our direction vector a, b. So instead of writing it like this with whole vectors, we can also write what's called the parametric equation, just pulling apart the x components and the y components of each vector. So x would equal x naught plus t times a, and y would equal y naught plus t times b. So this will hopefully kind of help you see that we can write it in two different ways, and it will be easier to see that with a numeric example. Okay, the last form of the equation of a line in R2, and this goes back to our very first original equation, this 3x minus 2y plus 6 equals 0, is the Cartesian equation. It's also sometimes called a scalar equation because it has scalar coefficients of x and y variables. So this is the standard form of an equation of a line that you guys have been doing since grade 9. And I just want you to kind of take a look at what vector, if we took the vector with the coefficient here of the x and the y, so vector 3, negative 2. And we know that a vector in the direction of this line was 2, 3. So we knew that our vector M was 2, 3. So what do we notice about these? The direction vector along the line and the vector given by these coefficients. I hope that you guys can see, if you looked at the slopes or if you looked at the measurements or even just kind of eyeballing it there, these are actually going to be perpendicular. So that's an important term. The perpendicular vector is called the normal, and that's always going to be the case. So the vector AB is perpendicular to the line. And if we wanted to prove that, we can kind of, I don't know, this isn't quite a proof necessarily. We can put this into y equals mx plus b. So if we had ax plus by plus c equals 0, by equals negative ax minus c, and then y equals negative a over b x minus c over b. So here, this slope is negative a over b. So that means the negative reciprocal slope is b over a. And I think that you guys can see that this is the rise here and the run. So if we had a rise of b That's my y value, right? And a run of a, that would be vector a, b. So the run is the x component and the rise is a y component. So just kind of looking at the negative reciprocal slopes, which you would have done in grade 9 and 10, we can see that this is always going to be the case. So that tends to be pretty important later on, especially in the end of this unit. We're going to